Hello guys, so this is lecture 4.1 and I will talk about Catalan numbers. So this is the next topic in the sequence of combinatorial and generating function stories. And so the whole lecture 4 will be devoted to things related to counting trees. And I want to start with Catalan numbers because they are probably the most fascinating example of that. So these are these numbers Cn. And you have already seen that. So one of the ways to interpret Cn is to take a1 up to n plus 1 letters and put brackets in some way. So for instance, C3 is equal to 5, and this is because if you have 5 letters, there are, four letters. Oops. 4 letters, there are 5 ways to put brackets between them, like this. So you have seen that already. So I'm not going to use this interpretation, I will use another one. And one of the problems in the next piece that will be to construct explicit bijection. But so today we will instead work with other way to think about Catalan numbers. So Cn is by definition number of triangulations of a convex n-gon by diagonals. So what I mean by that? So you take a convex n-gon, you can take even a regular n-gon, that doesn't matter. And then you want to draw a bunch of diagonals so that they cut it into a triangle, into triangles. And if you just look at the sum of angles, you know that for each of them you have pi, and then it is an easy exercise that for an n-gon it is pi times n minus 2, n plus 2 gon. So sum of angles of the whole polygon is, as one can show by taking any particular triangulation, is equal to n times pi, and so it means that in any triangulation you will have exactly n triangles. So you are allowed to use only diagonals, and you want these diagonals not to intersect. One can characterize this by just saying that you have a polygon and you take a subset of diagonals which has n elements and where they don't have a common interior points. That's also a possible definition. So anyways, and then the statement is that actually counting triangulations of n plus 2 gon is the same thing as counting bracketing expressions of n plus 1 letters. And this will be a homework problem, but let me maybe just give you one example of sort of how this bijection works to give you a little hint. So let's see. So basically, that's too complicated. Let's do a 5 gon example. Sorry. So you put this A1, A2, A3, A4 on sides, and then you have some triangulation, and then basically you use each triangle to write down the product on the third side, A3, A4. And then you write here A1, A2, A3, A4. So please figure out the remaining details, why this is the same thing. It is easier to think probably about triangulations, it's more intuitive. And just very quickly, so if you take C2, this equals to 2. And the reason is that there are 2 triangulations like that. C1 probably should go first as 1 because there is just 1 triangulation. And C3 equals to 5, and the reason is that there are actually 5 triangulations of a 5 gon where you choose just some point and all diagonals go outside. So this is 1, 2, 3, 4, 5. Okay, So this is these are the pictures, and the main goal is to find a formula for Catalan numbers. And my goal is to prove the following theorem. So theorem is that actually there is a formula, the Cn equals 2, and then I hope it is 1 over n plus 1 to n choose n. Let's see whether I'm right. So if you take C2, then you have 1 over 3, 4 choose 2, and 4 choose 2 is 4 factorial over 4 is 6 is equal to 2. Yeah, I guess this is right. So this is the result. And if you think about it, it's totally not obvious, and the formula is surprising. And even the fact that this binomial coefficient is divisible by n plus 1 is kind of miraculous. Why it should be? I mean, this is, you know, n to n factorial divided by n factorial n plus 1 factorial. So why this is even an integer? That's already a non-trivial. So I'm going to prove this theorem. Moreover, I will kind of explain to you a way how to come up with this formula if you don't know it, which is even more remarkable. The result is actually due to Euler, so he was able to count this number of triangulations. And by the way, let me maybe just say a few more things. So there are lots of different interpretations of Catalan numbers, and one of them is this bracket structures, another is this triangulations of a polygon, and another one is you can take instead a 2n gon and draw non-intersecting diagonals where they don't have even common vertices. The number will also be Catalan numbers and some others, and there will be a few homework problems about that. Every time you can find an explicit bijection between different interpretations. So the result is actually due to Euler. So of course, how are we going to solve it? So we will form a generating function. So generating function, and this generating function will be something like whatever, f of x equals sum from I equal 0 to infinity Cn x power n. Right. By the way, is C0 equal to 1 or 0? Let me think for one little second. Okay, yeah, so we also put C0 equal to 1. So C0 is 1, and this is in agreement with this formula, of course. No, it's not. Anyways, so C0 is 1. Okay, so let's see. So now my goal is to find a formula for a generating function. And so let me maybe just, it is always helpful to just remember the first several terms. So it equals to 1 plus x plus 4 plus 2x squared plus 5x cubed and so on. So how one can possibly find a generating function for a sequence? Of course, the idea is to use some kind of a recurrent relation. So probably this number Cn satisfy a certain recurrence, which also would help to compute them. And indeed, this is the case. So let's try to understand what the recurrence relations they satisfy. And the idea is, let's just look at that. So suppose we have a 6 gon, or like 7 gon. Let's take 7 gon. 1, 2, 3, 4, 5, 6, 7. So how would I count a number of triangulations? So the idea is as follows. So we are going to find what is C7 gon, C5. Okay, so the idea is as follows. So let's choose some side, which will be our kind of base side. Let's suppose it is this one. And then we know that definitely it is a side of one of the triangles in the triangulation, just because, I mean, we cut it by diagonals into triangles, and we know that every side is a side of one of those triangles. So, and then there are several options. So this triangle can be this one, or it can be this one, or it can be this one, or it can be this one, or this one. So if I label it 0, 1, 2, 3, 4, 5, 6, then basically there are choices where there triangle 0, 1, 6 is adjacent to 0, 6, 0, 2, 6, 0, 3, 6, 0, 4, 6, 0, 5, 6. And then, so if you pick one of these choices, then what happens is that basically to triangulate the whole polygon, you have already found this triangle, and then you need to triangulate two parts of it. So this part and this part. And we know the number of ways to triangulate them. And of course, if you, so this is a bijection between triangulating the whole polygon, or choosing one triangle and then triangulating both of these two polygons on left and right. And this, of course, leads immediately to the recurrent relation, which is, in this case, C5 equals 2. So if I choose 0, 1, 6 triangle, then there exists a unique way to triangulate the two-gon 0, 1, which is basically empty, and this is C0. And then we multiply it a number of ways to triangulate the remaining part, which is a 6-gon, which is C4. But also one can use triangle 0, 2, 6, and then we need to add C1, the unique triangulation of 0, 1, 2, what is to the left, times C3, unique triangulation of the remaining part. And similarly, we have C2 plus C3, C1 plus C4, C0. And this is a recurrence relation, so now we can compute C5 if we know all previous stuff. So, in general, we have Cn plus 1 equals to sum Ci Cn minus I from I equal to 0 to n. And again, so the formal proof will be, so if I want to, so the formal bijection is as follows. So we assign, so we take a triangulation. So this one is triangulation of n plus 3 gon, and we send the triangulation of n plus 3 gon to a triple. So the first element is number I from let's see, from so it's n plus 3 gon. So number I is from 1 to 5, and so if I label. Okay, let me write down the whole proof again. Okay, so let me prove the general statement. So lemma for any n greater or equals than 1, Cn plus 1 equals to sum from I equal 0 to n, Ci Cn minus I. Okay, so I want to construct a bijection between triangulations of the n plus 3 gon and pairs of two triangulations of I plus 2 gon and n minus I minus 2 gon. So for this, let me just draw this n plus 3 gon, and I will maybe introduce some notation. So this will be vertex A and this will be vertex B, and then I will just label them from 0, 1, 2, and so on up to n, and then I have n plus 3 vertices. Perfect. So now I want a bijection between two sets. So my one set is a set of triangulations of an n plus 3 gon and so this is the set of triangulations is just something with this cardinality. So here cardinality equals to Cn plus 1, and then I will take a union over I from 0 to n, and for each I from 0 to n, I will take a set of triangulations of now let's see, so I equal to 0, this is 2 gon, I equal to, so I want Cn minus I, so of number of triangulations of an I plus 2 gon, and similarly times number of triangulations of n minus I plus 2 gon. And of course, by this I mean kind of disjoint union, so just take this sets and take their union, so the number of elements will sum up. And here the cardinality is Ci, here it is Cn minus I, of course. So how to explain what is the bijection? Okay, and what this bijection does, so it takes two triangulations, and then it takes a triangulation of our triangle, of our polygon by a triangle ABI. So this is one of the triangles, and then I have, I use the triangulation of I plus 2 gon, so this one is an I plus 2 gon, and this is an n minus I plus 2 gon, and so I can use this triangulation to triangulate this one, and this triangulation to triangulate this one. And so for any I choose one triangle here and use these two triangulations to construct triangulation of the whole n plus 3 gon, and vice versa. Every triangulation of an I plus 3 gon, you can look at the triangle adjacent to the side AB, and then look at the corresponding pair of two triangulations of the remaining parts. And this is a bijection. So this proves this beautiful recurrence relation, and now we can use it to write down an equation for the generating function. And of course you see that it behaves as if we need to take a square of it, because if we take a square of the function, we will start to see Sn Si times Sn minus I as a coefficient. So let me actually do that, and I will erase everything except the generating function and lemma part. And please remember the statement of the theorem. Okay, so what do I do? So let me compute the square of my function. So again, I just see that this reminds me of a product of two polynomials. And of course it has a formula. So I will see here C0 times C0 plus C0 C1 plus C1 C0x plus C0 C2 plus C1 C1 plus C2 C0x squared, and so on. And of course that's nothing but, if we apply this formula, that's C1 plus C2x plus C3x squared plus and so on. And you see that we get almost the same equation as this one, except shifted by 1. And then let's just reconstruct it. So if we multiply it by x and add 1, then we will have, of course, 1 is C0, so we will get C0 plus c1x plus and so on. And this is, of course, f of x. Okay, so f of x can be found from this equation. And then, I mean, we can rewrite it. So x f of x squared minus f of x plus 1 equals to 0. And it is not hard to find a solution. So the idea is that you can absolutely use the usual formula, for quadratic formula, for solving quadratic equations. So let's see, f of x will give us minus 1 plus minus, and then it should be square root 1 minus 4x divided by 2x. And so basically there are two functions, one minus square root, one plus square root, satisfying this relation. And I mean, of course you might worry whether you can just do all the separations with functions, but I mean, after all, so I will talk about the square root, but there exists so you can easily show that if you have any equation f squared equal to g, where g is a generating function a0 plus d, where this thing is non-zero, then this equation has exactly two roots. One of them will start with square root of a0 and another with minus square root of a0. And the proof is exactly the same as the proof which we had before of, for instance, the fact that you can invert power series. So with formal power series, you can solve quadratic taking square root if your power series starts with anything which is non-zero, and you can extract square roots, which we can do. So let's try to, I mean, we can, so for instance, this is true for this function 1 minus 4x, and square root of 1 we choose equal to 1, and then we get that. And so since such function exists, there is no question of existence. Every formal power series, you can write any sequence, it exists. So then we know that it should be one of these two. And of course, just looking at the first few terms, we will see what sign to take, and the answer will be plus. But to actually compute it, let's talk about square root of minus 4x for a second. So for this, let me just maybe say one more thing. So let's consider the following power series. So it will be denoted by 1 plus x power alpha, and it equals to the following. It equals to alpha choose 0. I will explain everything in a second. Alpha choose 1x, alpha choose 2x squared, plus and so on. So of course you can see here something looking like binomial formula. So this is not a number. So I take x and alpha as variables. So you can think of them as polynomial variables, just as polynomials. And this is a power series in two variables, if you wish. So one of them is x, and another is alpha. And alpha choose k is just this polynomial alpha choose k, which we already have seen, alpha times alpha minus 1 times alpha minus k plus 1 over k factorial. Let me check. So and minus 1 over 2. Yeah. And so each term here is a polynomial in alpha, and in general you can think that this is a power series where coefficients are polynomials in alpha, which is of course fine, or you can think of it as power series in two variables, because of course you can write it down as some coefficients times x n alpha power m, and for every power of x you will see powers of alpha which are less than n. So and this thing is again a formal power series, and it has a main property. So lemma, which is an easy one, is that 1 plus x power alpha times 1 plus x power beta is equal to 1 plus x power alpha plus beta. So again, so we know that this is true for binomial formula, and one can just generalize the proof and prove the correspondence. So this will lead to some equality for these polynomials alpha choose k, depending on variable alpha, and beta choose k. And I will leave it as an exercise to you. And then, of course, this implies, for instance, that if I take 1 plus x power 1/2, and this is just, 1/2 0 plus 1/2 1x plus and so on, then it has a property that if you square it up, you will get 1 plus x. And what it in particularly means, it means that if you have a square root of 1 minus 4x, so square root 1 minus 4x, we know that there are two power series like that, and they will be different by sign. And so this actually, the one which starts with 1 will be, let's see, so for this I just take this power series and plug in minus 4 instead of x, so this will be still 1/2 choose 0 plus 1/2 choose 1 minus 4x plus 1/2 choose 2 minus 4x squared plus and so on. And this one starts with 1 because this is 1, so this is the choice of a square root which starts with 1. Oh, sorry, and here I will take, I have to take minus sign, because if I take plus, then it will not start with something. I will not be able to divide by x. So sorry, this is minus. So this one will be the square root. So there are two square roots, and they both satisfy this equation, but if I take, instead of minus, I take plus, then what will happen is that it will start with 1 over x, so it has this term which is not allowed. So I know that my power series should start with 1, and so I need to take minus here. Okay, and the next question is, of course, to compute what the sum is. And now, I mean, this already gives me a formula for Catalan numbers, and if I just think about it, so this implies the following formula. So if I have my Cn, so Cn is a coefficient before x power n in this function, which is a coefficient before xn plus 1 in this function, and this is just minus 1/2 choose n plus 1. Sorry, let me write it down here. So Cn, so this is n plus nth coefficient of this power series. So here I divide by x, so it is n plus first coefficient of this power series. And for this I need to, so this is 1/2, it doesn't matter, it's 0 coefficient. And then I have minus square root over 2 square root, so I need to take n plus first coefficient of a square root, which is 1/2 choose n plus 1, and then minus 4 power n plus 1, multiply by, okay, 1/2 choose n plus 1 minus 4 power n plus 1, and then I need to take minus sign here and divide by 2. So that's the formula. And of course, I was a little bit floppy with this 1/2, 1 over 2x, but this 1 will be killed by 1 coming from here, and so it doesn't matter. So this is the formula, and of course it looks terrible, so let's simplify it. So I will erase now this part. Okay, so let's simplify it. So minus, so let's see what is 1/2 choose n plus 1. So this is, of course, according to the formula, it's 1/2 minus 1 product up to 1/2 minus n divided by n plus 1 factorial, which equals 2, and then it is 1 times minus 1 times minus, so minus 1, and then it will be 1/2 minus 2, which is minus 3, up to 1 minus 2n over 2 power n plus 1 factorial. Okay, so then I will multiply on n factorial and n factorial both parts. So then what this equals to. So first I will collect all the minus signs, and this will be minus 1 power, here I have, let's see, 1, 3, minus 1 power n, I think, right? So if n equals to 1, this will end here, and I will have minus sign, minus 1 power n. So then I have, and then I will have 1 times 3 times and so on up to 2n minus 1 times, and then I want to add here all other products of even numbers. So I can say that I multiply it by 2, 4, and so on up to 2n, but I divide by 2 power n. So instead of n factorial, I wrote the product of all even numbers divided by 2 power n. And here I have times 2n plus 1 times n plus 1 factorial, n factorial, which equals to minus 1 power n times 2n factorial over n plus 1 factorial and factorial, sorry, it's a factorial, 4 power n times 2. And let's compare it with what we want. So we need to multiply on 4 power n plus 1 minus 1 power n, because there is n plus 1 here and minus here. So then it means that Cn is equal to 2n factorial over n plus 1 factorial n factorial. And then, so I divide by 4 power n plus 1, because I divide this by 2, and I multiply on 4 power n plus 1, which will cancel out. And sine is here minus 1 power n, and here it's minus 1 power n plus 2, and that's also cancel out. And so the answer is 1 over n plus 1, 2n, choose n. And this proves the statement. So let's again go through the idea. So we started with saying we have a sequence, it has a generating function, one can try to compute it. Then we figured out that there is some interesting recurrence relation for Catalan numbers coming from geometry. And then we were in business, we just used it, we saw that there is some pattern reminding of a product of 2 power series, and then we saw that one can square up the power series and get something very close to these numbers, which implied a functional equation for the generating function. And then we know that this functional equation, it has a priori 2 solutions, with minus and with plus sign. One of them doesn't work because it will start with 1 over 2x, 1 over x, and in the other there is a normal generating function. Since we know that our function satisfies this equation, it should be one of those. And then the question was, okay, here is the function, how to write down explicitly the power series. And for this we used the power series for square root of 1 minus 4x, which again I understand is a power series whose square is 1 minus 4x and which starts with 1. And then here is this power series. So, and then we just computed what this polynomials 1/2 choose k equals to? And the answer is that there is a beautiful formula which you can actually remember. You can remember that for this 1/2 binomial coefficients, so kind of a version with 1/2, there is a simple formula which writes them down as something meaningful. So basically all these denominators go away, and that means that implies the statement and the formula. So I think this was the way Euler solved it, which is, I guess, remarkable. And also let me add one more thing. So if you are working with analysis, if you care about convergent series, then you can actually say that 1 plus x power alpha is convergent for alpha less than 1, absolute value of alpha less than 1, and I guess x should be less than, absolute value should be less than 1, and then actually one can prove that 1 plus x power alpha is the sum of this power series, and then one can think that we just operate with, convergent power series and use it. But again, I never needed anything like that. So here we finish the Catalan number story, and there will be several problems about them in homework. So all problems about Catalan numbers are not so easy. So start with maybe drawing some pictures and looking at concrete numbers, and then find an explicit bijection. You can also look for this equation. It might help to understand where the statement comes from. And also there will be some problems about power series kind of coming from this statement. Okay, so next time we will talk about graphs and trees for a little bit, and in the last part of this lecture we will apply this to counting certain types of trees, maybe labeled trees, and prove Cayley's theorem about counting of labeled trees. And after that we leave this generating functions story for a while, though there will be more problems in homework problem sets, and we will go to complex numbers and the fundamental theorem of algebra.